Hello and welcome to another power electronics class. In the previous class, we solved some examples of voltage regulators and how we can reduce the voltage using different methods such as voltage divider and Zener diodes or voltage regulators. And we solved them to find the efficiency. And when solving the efficiency problem, we realized that switching has the maximum frequency, the maximum efficiency. Ideally, it's around 100%, but obviously we don't have ideal switches, so it's going to be less than that. But the other methods in this case scenario, they have around 50% efficiency, so it's much more efficient. And as you know, if you have high efficiency, you have lower loss, creates less heat. So you need less components. You don't need a heat sink. The design is going to be much simpler and so on. So the way to go is to use switching. I already also spoke a little bit about pulse width modulation. I'm going to continue that today. And then we're going to start on the duty cycle, the definition of duty cycle. How does a switching system even work? And if we have time, we're going to start with DC to DC buck converter. So as we learned from the previous class, the pulse width modulation, PWM, or sometimes they call it the pulse duration modulation, PDM, is a commonly used technique for controlling power in electronic devices. And the way that they work, we have a switch and we control the duration when the switch is turned on or off. So this is a PWM, and by controlling the width of when the switch is on or off, we control the output. In a PWM system, the frequency must be much higher than what would affect the load. So usually because we want to convert DC to AC, depends on what is the output frequency that we want. So for example, if we just want to do from DC to AC, we can use a 60 Hertz PWM system. If we want to do a pure sine wave, that's a different story. I would explain more about that. The main advantage of PDM or PWM is the power loss. In these systems, it's extremely low, and I explained why in the previous class. They are not only used in power electronics, they're also used in communication systems. It's a type, initially, it was mainly actually used in communication systems for sending data, transmitting data. And then the applications in power electronics were expanded that much that you see that now both in, again, communication systems and also in power electronics. So the way that they convey a message, we know that in a communication system, and when you want to communicate data, we have the data in bits, zeros and ones. And a PWM, we can show zeros with this. For example, a pulse that has the width in the zero part and the off part is more than the when it's on. So this is going to be 0. This is going to be, for example, another 0. And then we show the ones with a pulse that has a higher width. So imagine, and then this is R1. So I'm going to do it with a different color. These are going to be R1s. So 0, 0, and 1, 1. So by changing the pulse width, for example, if the positive pulse is more than 50%, then it's a 1. If the negative pulse is more than 50%, then it's a 0. Where do we use this? As I mentioned, RC cars, okay, remote controlled cars, they use a PWM for communication as well. And the good thing about this is we can expand. Instead of having a single bit zeros and one, we can have like a 2-bit system. So 0, 0, 0, 1, 1, 0, and 1, 1. How can we do that? So for example, this is 0, 0, for example, and this is 0, 1. This one would be, for example, 1, 0, and this one would be 1, 1. So by changing just the width, instead of sending single bits in one period, we can send 2 bits. Therefore, we can, for example, double our bandwidth. We can send more data. Where do we need this? When we want to have a communication system like a mobile phone or smart, well, when we want to communicate, for example, in Bluetooth or Wi-Fi. They don't actually use this, but this is just an example. And you need a higher bandwidth because you want to send a video or a picture. Then you can actually have, instead of single bit, you can have double a 2-bit system and so on. And you can double the bandwidth. So some definitions of a PWM system. The duty cycle is called D, and this is very important. And the duty cycle in a PWM is equal to the on time over period. In these systems, VLOW is often 0, and the average voltage is going to be equal to dV high plus 1 minus dV low. Now, can you tell me how can I find period here? What is period in this equation? So the period here is the on time plus the off time. Yes, the total period here is the on time plus the off time. On time plus the off time. Okay. So let's solve a simple example. In this particular case, imagine we have this graph. The on time is 4 seconds, and the off time is 6 seconds. The high voltage is 5 volts. I want you to find the average voltage. I'll give you a few minutes to think on this. First, you need to find D, and using this equation, we want you to find the average voltage. So 4 second on, 6 second off, it means it's turned on 40% of the time, turned off 60% of the time. Here, this is 5 volts. Yes. And it shows here that VLOW, you can see VLOW is actually 0 volts, 0% or 0 volts. I'm sorry. So First, D, we have to find T. It's going to be the on time, which is 4 divided by the period, which is on time plus off time. So D would be 0.4. A quick note over here. What is the range of D? What is D between? Is it between like -1 and 1, 0 and 1? What is the maximum that D could be? The minimum that D could be is when on time is equal to 0. Yes. So if it's completely off all the time, then D would be equal to what? 0. What is the maximum that D could be? Yes, when on time is equal to period. This is the max that it could be. And in that case, D would be equal to what? 1. So D is always between 0 and 1. It can't be greater than 1. Obviously, we can't have more than 100%. Can't be. Okay. Just a quick note over here. Now D is 0.4. So V average would be equal to 0.4 times V high, which is 5, plus 1 minus 0.4 V low. And since V low is 0, second part is going to be 0, and this is going to be equal to 2 volts. Now, what if on time was 5 seconds? What would average time be? So if the on time was 5 seconds, then D would be 0.5 of or 50%, and V average would be half of the maximum, which would be 2.5 volts. Okay. So the higher the duration is, the duty cycle is, you're going to have a higher voltage. If the duty cycle is 1, the average voltage would be 5 volts. If the duty cycle is 0, the average voltage would be 0 volts, because it's going to be, so if it's 1, meaning it's turned on all the time, and if it's 0, it means it's turned off the time. This is 0, this is 1 when duty cycle is 0. Now, let's look at the generation of PWM. This is how we generate a PWM signal. Just go back. Did you write this down? Yes. Okay. So again, if duty cycle is 1, the average voltage would be 5 volts. If it's 0, it's going to be 0 volts. And duty cycle is between 0 and 1. Now, how do we generate a PWM signal? This is an example of an analog to PWM conversion. And usually for the conversion, we use a comparator. Let's go and let's do a quick review on a comparator. Do you remember what a comparator was? A comparator is a type of op amp, okay? We had the supply voltage V and positive V. And we had 2 inputs. We had the inverting input, let's say this is the inverting input, and the non-inverting input. Do you remember? For an ideal op amp, what was the gain for an ideal op amp? Thank you, infinite. Okay. And V out would be AV, the gain, times V positive minus V negative. Am I correct? This is what was for an ideal op amp. without any feedback, okay? So now imagine if V positive is connected to the ground, and I give a small sinusoid, or let's say a small triangle signal to the negative. And my positive voltage is 15 volts. My negative voltage is negative 15 volts DC. What would the output look like? So since this is infinite, technically, in theory, it's infinite, but technically in reality, what is our maximum voltage that the output could be? What is the maximum minimum voltage that the output could be? What is V out max and what is V out min? So in real world scenario, the maximum voltage that the output of an op amp could be is equal to its power supply, okay, or the supply rail voltage. It cannot be more or less than the supply rail voltage. If we could do that, we would connect a AA battery to an op amp and generate 10,000 volts, for example. This is not at how it works. The maximum voltage, output voltage that an op amp could have is limited to its power supply, the supply rail voltages. So the maximum voltage is actually in the real world, it's a few volts under 15, but I would assume this is an ideal. So this is positive 15 and negative 15, for example. But in the real world, it's actually a few volts below that because you have losses in the op amp. We don't have an ideal op amp. So in this case, V out, if V positive is greater than V negative, it will be equal to what? So if V positive is greater than V negative, and we have F infinite, which is an V positive minus V negative, and if V positive is greater than V negative, oh, by the way, this is a non-inverting amp. This is an inverting amplifier, so it's going to be V negative minus V positive. So in this case, if V negative is greater than V positive is greater than V negative, then we're gonna have a negative VCC or VCE, let's say, in the output. If V out would be, if V negative is greater than V positive, then we would have a positive VC. Yeah. So as you remember, in an inverting amplifier, V out, you remember, if the negative input was greater than the positive input, then we would have a negative V out in the output. Sorry, I did it small. Yeah. And if the V positive was greater than the V negative, you're gonna have a V positive. Now let's see. So a competitor, as mentioned, simply what you have, or to erase confusion, let's make it like this. And let's go back here. So in a competitor, in an ideal op amp, again, AV is infinite. Therefore, if V positive is greater than V negative, we're gonna have a positive output. If V negative is greater than V negative, we're gonna have a negative output in the system. Now imagine we have two signals in the input. So instead of having one of them as a DC, as a flat, 0 volt or something like that, that creates a threshold, we have two different signals. The first one is a triangle, and the second one is, or the first one is a sinusoid, the second one is a triangle signal. And what happens here is, again, when V positive is greater than V negative, so here, since that is connected to the inverting input, we're gonna have 0 in the output. And when V negative is greater than V positive, I'm sorry, V positive is greater than V negative, the sinusoid is V positive, then we're gonna have positive output. So you can see that when the sinusoid, the amplitude gets higher, you're gonna have a pulse width that has a higher width in the positive side, and when it gets lower, you're gonna see that it has a width that it's the higher width in the lower side of the system, on the negative side of the system. Now, by changing the frequency of this F, you can change the frequency of the bandwidth. Higher frequency, you're gonna have high frequency. And by changing the shape of that, the first one, you can change the width and the duty cycle of the output. So instead of, let's say, this sinusoid, if I had something that looked like this, then I would have a signal that had a higher width in the negative part, because this is connected to the inverting side of the system. Is it clear? So the main point here is that a PWM pulse width modulation, we usually use an op-amp comparator to determine the duty cycles. And we can control the frequency of the duty cycle or the duty cycle itself by alternating the inputs, one of the inputs or the other. So this is another control system by pulse width modulation. We control the switching speed here, and by controlling the switching speed, we can control the average voltage, the duty cycle, and the average voltage. So when this is connected here, we have the on time, IDA goes to IA. And when it's disconnected or connected to the second one, I'm going to do the second one with a different color. When it's connected to the second one, then we have the off time. So I'm going to do the on time with red and the off time with blue. And again, duty cycle would be T on, or here T up, over the period, which is T on or T up plus T off. And the same that we had there, P average, V average is going to be equal to dV high plus 1 minus dV low. If the on time is higher, you're going to have a higher voltage, average voltage. If the off time is higher, so instead of that, if we had a signal that looked like this, and the off time cycle is more than the off time, then you have a lower average voltage that it's around here. Now, quiz number 1. In the switching power pole, the duty ratio D waveform pulsates between 0 and 1. Is that correct, or is it true or false? Yes, correct, it's true. So the duty ratio, as you know, it's T on over period, which is T on plus T off. The maximum that D could be, again, when T on when T off is equal to 0. It's when T off is equal to 0. So it's going to be T on over T on, which is 1. And the minimum that could be is when T on is equal to 0. So this would be equal to 0, as I mentioned before. So D is pulsating between 0 and 1. In a switching power pole, VA waveform alternates between 0 and the input voltage level. Is this true or false? Yes, correct, it's true. What is the maximum output voltage? The maximum output voltage would be when D is equal to 1. Okay? When D is equal to 1, VA would be dVH. Because when this is 1, this would be equal to 0, and this is again 1. So VA would be V high. Okay? Or it's going to be input, which is the maximum of the input. Let's say Vn. And the minimum that could be, again, is when D, this is equal to 0. When this would be equal to 0, this is 0, so it's going to be 1 V low. And if V low, we assume it's 0, then VA would be equal to V low, which is equal to 0. So it's pulsating between 1 and 0. I'm sorry, between the input voltage and 0. Now, the circuit implementation duty ratio control switch, or what we call the SPDT. The SPDT switch changes DC components. All power semiconductor devices act as a SPST switch. The switch output voltage waveform, the duty cycle is between 0 and 1 again, and the complement or D prime is equal to 1 minus D. Again, this is the schematic of a switching system. DTS is the on time. And D prime TS is the off time. Now, let's find the average voltage. Imagine that we have this graph. How can I find the average voltage here? I mentioned this in the previous class. How do we measure average voltage in the signal like this? We measure total area under it, yes? How do we calculate the total area on the graph? Use integral, okay? So to find the DC component or the average voltage, average value, we need to find the area under the signal. And since this is a square signal, what is the area under the signal? It's going to be this multiplied by, so that's going to be Vs times dTs. Yes, okay. So Vs average is 1 over Ts, because we want to find it in one period, by the way. The integral from 0 to Ts, Vs t dt. So Vs t dt is going to be d Ts Vg. By the way, we want to find it in Ts in one period. So Ts and in the denominator and the denominator cancel each other out, and we are left with dVg. And it's going to be Vg. But the problem is that Vs average is not always equal to dVg at all the time, and I'll explain why. Because we don't have this graph is for when we have an ideal switch, and in real world we don't have ideal switch, and we don't have a square signal. In real world, I would explain later that the signal looks something like this. So the first type of converter, DC to DC converter, we already learned about all the concepts of PWM. And why do we use switching in PWM? Because of their high efficiency. And what is a duty cycle? Now we will start with the first type of DC to DC converter, which is called a step down or a buck converter. So a step down is a buck converter is a type of switch, and we usually have a DC filter as well to filter out the signal. And by controlling the duty cycle, we could control the output voltage. The reason that we call it the step down or a buck converter is because V out is always less equal to Vn. In an ideal situation is Vn, but it's almost always lower than Vn. It's reducing the voltage in the output, therefore we call it a step down converter. So a step down buck converter or a buck converter has different components. The most important part is the switch. I'm going to show it with SW. Then we have the low pass filter. And I mentioned low pass filter in the previous class as well. If the system is in position 2, allows for current freewheeling. So the current just goes through when it's connected to number 2. And V out can be controlled by adjusting the duty cycle or the switching period, and V out over Vn in this situation is equal to D. In an ideal situation, we have no switch loss. The efficiency is 100%. And to make it easier for now, we assume that we have an ideal switch. Summary of example. This buck converter exemplifies how waveform chopping allows control output. Waveform modification bar chopping is fundamental is a fundamental premise in power electronics. In an ideal switch situation, we have no loss. Controlling D controls the output voltage. And this system is independent of load. For an ideal switch, this is example, this is the one that we showed as the best approach. In real world situation, the switch is not ideal. We have switch loss, resistance in the system, and the transition time as well. And chopping means harmonics at both the input and output. And is the assumption of an ideal switch reasonable, you think? For this case, for solving it, we use the assumption, but in real world, and I'll explain more that we use a real world model for these switching systems. So to better understand these an ideal situation, we need to go back a little bit and do a quick review on semiconductors and how we build these switches, the fundamentals of these switches. These switches are mainly made out of semiconductors. They are mainly made out of thyristors, transistors, and diodes. They have different voltage ratings, current ratings, switching speeds, and on-state voltages. In an ideal switch, we have some characteristics of an ideal switch. We have zero on-state resistance. So for example, if I have a diode here, when the diode is in forward bias, the forward bias resistor, I'm going to call it RF, is going to be equal to 0. So imagine if this is a diode in forward bias, the resistance is equal to 0. Meaning V, the forward voltage, is going to be equal to 0. So we're going to have no forward voltage loss. But in real world scenario, do you remember what was the voltage, the forward voltage bias voltage for a diode, the on voltage? For a silicon diode is 0.7, 0.6. And for a germanium diode was 0.3 volts. If you had electronics lab with me, you remember that just for turning on a diode, you need 0.7 volts to turn it on. But in an ideal switch, we have no forward voltage drop, meaning V forward is going to be equal to 0. And as you remember from the diode graph, that looked a little bit like this. We also had a reverse voltage as well. It wasn't a linear graph. And when it was in reverse bias, we had a little bit of leakage voltage and leakage current here as well. And this leakage current was around a few milliamps. This over here was our leakage current. Meaning when the system was in reverse bias, we still had a little bit of current trickling through the system. That current was pretty low. It's like a faucet that wasn't completely closed. But an ideal switch, which acts like a switch, you would have no leakage current. So in reverse bias, you don't have any current passing the system. In an real world scenario, we didn't have a limitless diode. If you put too much reverse current into diode, we would go into the Zener zone and you will break down the diode. You can't put infinite voltage in reverse bias in a diode. Diodes have a limitation around 50, 60 volts. For a normal silicon diode, signal diode, power diode is higher. But the current has limits in a real world diode. In an ideal switch, we have current limitless when on either direction. The conduction current is a function of external components only. We have no limits on amount of voltage across switch when it's off. The blocking voltage is infinite, forward or reverse, but in real world, you know that if you put too much current in, it's just gonna break down. It's gonna destroy the diode. And the other thing is the switching can transition from on to off or off to on instantaneously when commanded to. But in real world, we know that we had a depletion region and a PN junction transistor. And it took some time for this depletion region to expand and for the holes and the electrons to move from one side to another. Therefore, we had a transition between on and off. And in real world, you can see that we have this transition between on and off as well. The current voltage characteristics of an ideal switch. In an ideal switch, we'd have no power loss because we don't have any leakage, we don't have any conduction loss, we don't have any forward bias voltage, none of that. And the switch transition, we have no overlap. Therefore, the voltage of a switch when it's on, V positive minus V negative is going to be equal to 0 because V positive is equal to V negative. Therefore, when it's on, V on for a switch is going to be 0. And when it's off, the current passing is going to be equal to 0 amps. And when the current passing is 0 amps, this is like an open circuit, and V open circuit is equal to the maximum voltage or the input voltage. So as you can see, the power loss is 0. So the power in the switch is 0. The power of the switch is equal to 0. And since it's an ideal situation, when the switch is off, we have the maximum voltage. When it's on, we have 0. And the current would be 0 when it's off, and it's going to be the maximum current is going to pass when it's on, turned off. But in a practical switch, we don't have any of these characteristics. Although we had some advances and now we have very high efficiency, good switching devices, they are not ideal. We have limited conduction current when the switch is on, limited blocking voltage when the switch is in the off situation. Both are directional in practical switch. We have limited switching speed that caused by the finite turn on and turn off times. In real world semiconductor switches are charge driven, and it takes time, as I mentioned, for the holes and for the electrons to move and to saturate a PN junction, for example. We have a finite non-zero on-state and off-state resistance. There is a I square R loss when on and some leakage when it's off. It's usually very small. In real world, a practical switch current voltage characteristic looks like this. So first, this is the root cause of the signal, a single major source of loss in power electronic converters. So what happens is when the system is off, we don't have a zero current. We have a little bit of leakage current, which you can see here. These are the leakage current. And when we transition from off to on, we have a transition time, and it doesn't instantaneously go from off to on. It takes some time, and this time creates some loss in the system. And this is called the turn on switching delays. Depending on the switch that we have, this could be from microseconds to sometimes milliseconds and even sometimes a second, no? So it depends on the system and the sophistication. Usually if we have a signal diode, they have very high frequency response. A Pyre diode is a little bit, depends on how, what is the material that it's made of, how big the diode is, and so on. And also, when the system is in forward bias, we have a little bit of voltage drop in this system, and this is again another source of loss. So for example, for a diode, as I mentioned, it's like 0.7 volts. If you have like a 200 volt system, 0.7 is negligible. But if negligible, but if it's a few volts, then it's a significant part when we have a significant loss. So this is the V graph, and this is the I graph. And as you remember, for an ideal, it looks square. We don't have any transition times, but in non-ideal, we have the transition times, and we had a little bit of leakage current when it was off. And the important part, the power loss was 0. But in an ideal situation, we have a switching loss, and the maximum loss is in the transition, in the delay time, when it's transitioning between the on and off, or from the off and the on. And the area under this is the amount of power that we are losing and losing in the system. We also have a little bit of loss in the system because of the forward voltage drop in the switch, and also the leakage current. And as you know, P is equal to VI. Yes. So if you multiply these two together, you're going to get the third one. Here, because we had ideal and it was the transition time was 0. If we had a voltage here, the current here would be 0. So V times I would be 0. And again, V was here 0, and we had I, and V times I again here was 0. But now here, when we are transitioning, we have a little bit of voltage and we have current. And when you multiply these two together, you're going to have the power loss in the system. Again, over here as well, we have this voltage and the current, and you can see the voltage going up, current coming down. So you're going to have the maximum peak at the middle of this graph, because after this point here, the voltage is dropping, and here the current is dropping. So the red area under the curve is the loss, the power loss in the system, or this what we call the switching losses, when switch is transitioning from on to off, or off to on. And the conduction was when the switch is in on state or off state to a lesser degree. Now, how can we reduce the power loss? How can we reduce P? I'm sorry? Yes. If we reduce the transition time, and if we use a faster switch, we can reduce this. Usually we can't do a lot about the leakage current and the forward voltage because they are the characteristics of diode, but most of the time we can increase the switching speed. It requires a more expensive switch, but we can go from a 20 cents diode to a $20 transistor or something like that. We can reduce that significantly, but still we have limitations. We can't take that to zero. We can't bring that to zero. So this is switching power pole in a buck DC to DC converter. This is an example of how it works. This system, again, we have a low pass filter, LPF. And this low pass filter, what it does is we store the voltage and the current. And when the switch is closed, we have the freewheeling of the current in the system. And here you can see the current that is stored in the system shown with IL. And you can see the input current IN. The graph on the top shows the QA, which is the charge in the capacitor, and charge is equal to CV. Q is equal to CV. Do you remember? Okay. So the voltage, when we connect the system and it's in on position, the capacitor starts charging and you have the current going up. And when you disconnect this, the capacitor discharges through the diode and you can see what happens. So V out here is going to be the average VA, and it's going to be the duty cycle DAVN. So input current is changing and going suddenly to zero, but in the output, because we have the storage elements, you're going to have a smoother output, getting the average from the current, and the average voltage actually looks like this as well. It's shown with dots. This is the average voltage in the system. Now in real world, we want to see how this switch part works. We want to know how to build the switch part. Usually we build the switch using transistors and diodes. This is an example of a transistor and diode forming a switching power pole in a buck converter. So the way that this buck converter works is when you give a signal to the transistor, imagine this is a BJT transistor and we give a signal to the base. Imagine we give this signal to the base. We turn on the transistor, for example. And when we turn on this transistor, this voltage V positive is greater than its V negative. Therefore, you're going to have the current going through the transistor and through the inductor and capacitor and to the load. Now imagine that you have 0 volts on the base. Now this voltage is less, sorry, V positive is less than its V negative. Now the diode is turned on, and when the diode is turned on, this is turned off. You're gonna have this loop over here. It's already mentioned it. And this would be turned off. So this is when the switch is turned on. This is when the switch is turned off. Now, how can we generate this signal? We can do it with a multi-vibrator. We can do it with a control system. And then we can control the on-off time. Okay. Is it clear how it works? Okay, so just by controlling the base voltage of a transistor, we can control its on-off time. I think it's... Now let's solve some practice problems for the same one. In the converter shown in the figure, the input voltage Vn is 20 volts. The output voltage Vout is 12 volts. We want to calculate the duty ratio dA and the pulse width T on if the switching frequency is 200 kilohertz. So from the previous equation, we know that Vout is equal to dA Vn, which is the duty cycle. And therefore, the duty cycle dA, the duty ratio would be equal to Vout over Vn. And our period Ts is equal to obviously 1 over Fs. And T on dA, again, the duty cycle, is going to be T on over our period Ts, which this is again as T on plus T off. I'll give you a few minutes. All the equations are given for you to find the on duration or T on. We already have Vout 12, Vn 20. You can find the duty ratio with that. We have the frequency. You can find the period with that. And then finally, you can find the T on time. Did you solve it? What did you get? Or you need more time? Okay. Did you solve it? What is? Yes, microsecond, yes. So dA is 0.6. Well, so it's gonna be 12 over 20. It's gonna be 0.6. And TS is 1 over FS, so 1 over 200,000, which is 200 kilohertz, gives us 5 microseconds. T on is equal to dA TS. dA is 0.6. And TS is 5 microseconds. So it gives us 3 microseconds. Check and see if it's correct. Yeah. 3 micro. Okay. Thank you so much. That's it for today. I would see you on Wednesday.